Hi everyone, this is Ashley Bedford, founder of the Runtime Diaries. Today we have a fun problem for you. This is day 29 of our hashtag 30 Days of Code Challenge with Educative. Today's question is binary tree cameras. Let's get into it.
Today, we're tackling one of those problems that feels impossible at first, but once you understand the underlying pattern, it becomes incredibly elegant. Binary tree cameras. LeetCode 968. This is a hard problem that combines greedy algorithms, tree traversal, and a brilliant three-state classification system. By the end of this breakdown, you'll understand exactly how to minimize camera placement while covering every node in the tree. Let's dive in. Here's the setup. We place cameras on tree nodes, and each camera covers three things: the node itself, its parent, and its immediate children. The goal is to place as few cameras as possible so that every node in the tree is monitored. This is a coverage optimization problem, and at first glance, it seems like you'd need to try every possible camera placement to find the minimum. If you try brute force, you'd have to consider exponentially many combinations. Why? Because placing a camera changes the coverage of its neighbors. One choice affects entire subtrees, and whether you place cameras high up in the tree versus down low dramatically changes the total count. This is actually a tree dynamic programming problem disguised as a camera placement puzzle. The key is recognizing that we can solve it greedily with the right approach. Here's where the problem transforms. Instead of thinking, where should I put cameras? You need to think, while unwinding the tree from bottom to top, what does each node need? This mental flip is everything. Once you start thinking in terms of what each node needs from its parent based on what its children reported, the problem becomes effortless. Here's the critical observation. A leaf node cannot cover itself and its parent at the same time. So what do? We avoid putting cameras on leaves. Instead, we place cameras on their parents. This reduces the entire problem to identifying which nodes force their parent to have a camera. And that leads us to a brilliant classification system with three states. Every node in the tree returns one of three states. State 0 equals not underscore covered. This means I'm not safe. Parent, please install a camera. State 1 equals has underscore camera. This means I put down a camera. You're welcome. State 2 equals covered. This means I have no camera, but one of my children covers me. These three states are the entire foundation of the algorithm. We must decide a node's state after knowing its children's states. So, we process the tree in post order. Left child, then right child, then current node. This allows a parent to react to the needs of its children. Post-order traversal is essential because information flows from the leaves upward to the root. After processing left and right children, we apply three simple rules. Rule 1. If any child is not underscore covered, this node must place a camera. Return has underscore camera. Rule 2. If any child has underscore camera, this node is covered. Return covered. Rule 3. If both children are covered, this node is not covered. Return not underscore covered. That's it. These three rules solve the entire problem. Let's walk through a simple example. We have a tree where the root has two children, and the right child has two more children. Post-order traversal Start at the bottom leaves. Leaves return not underscore covered. Their parent sees that its children are not underscore covered. So it installs a camera and returns has underscore camera. The root sees that one of its children has underscore camera and the other is not underscore covered. Therefore, it needs a camera placed. The minimal number of cameras emerges naturally from these local decisions. After the DFS returns, there's one critical check. If the root's state is not underscore covered, we must place a camera at the root. This is easy to miss, but it's essential. Don't forget to check the root. Here's the structure in pseudocode. We define a DFS function that takes a node. If the node is null, return covered. This is our base case. Recursively call DFS on the left child and right child. If either child is not underscore covered, place a camera at this node and return has underscore camera. If either child has underscore camera, return covered. Otherwise, return not underscore covered. This is a simple, recursive, and elegant approach. Here's the complete Python solution. We define 3 constants. Not underscore covered equals 0. Has underscore camera equals 1. Covered equals 2. We initialize cameras to 0. We define the DFS function with non-local cameras so we can increment the count. If the node is null, return covered. Recursively process left and right children. If either child is not underscore covered, increment cameras and return has underscore camera. If either child has underscore camera, return covered. Otherwise, return not underscore covered. After the DFS completes, if the root is not underscore covered, increment cameras. Finally, return cameras. This solution uses pure greedy DFS with O of n time and O of h space. Time complexity is O of n because every node is visited exactly once. Space complexity is O of h, where h is the height of the recursion stack. In the worst case with a skewed tree, this is O of n. In an average balanced tree, this is O of log n. This is optimal because you can't solve the problem without visiting every node. Here are the biggest pitfalls to avoid. First, forgetting to check the root after DFS returns. Second, treating none as not underscore covered instead of covered. Third, mixing up the child states and applying the wrong rules. Fourth, trying to solve this top-down instead of bottom-up. And fifth, placing cameras on leaves, which is always suboptimal. Most mistakes come from not fully understanding the 3-state system. Here's the mental model to keep forever. The parent covers the child. The child tells the parent what it needs. This problem is less about placing cameras and more about responding to subtree needs. This is a recurring problem in tree problems. Tree pruning, tree dynamic programming, coverage problems, and bottom-up greedy decisions. Once you internalize this pattern, an entire class of hard tree problems becomes approachable.
And that's a wrap for day 29 of our hashtag 30 Days of Code Challenge with Educative. If you like this video, like it down below, share it with a friend, and subscribe to our YouTube channel. We hope to see you again. Bye!